So we've been experiencing a technological revolution for the past 30 years. A supercomputer that used to cost millions of dollars and weigh multiple tons now fits in your pocket. We got here by shrinking the size of computer chips to the point where their smallest features are now only slightly larger than a single strand of DNA. This increasing computing power has benefits in basically every sector you can imagine. But if we want to continue this progress, there's some serious challenges that we need to overcome. To understand these problems a little better, though, we first need to understand how a computer works. So you may be familiar with binary, the language of ones and zeros that computers think in. But computers actually don't know what a 1 or 0 is. When they get a string of binary, what they actually see is a series of low voltages and high voltages. A low voltage is a 0, a high voltage is a 1. What this looks like for an electron moving through the system is I see a 0 and I stop. And I see a 1 and I go. And I see a 0 and I stop. And so now this should be throwing up red flags for all you Californians, because that sounds a lot like stop and go traffic. Only this is the worst traffic you could ever imagine, because it's a traffic jam that's happening 1 billion times a second. Just like a real traffic jam, this generates a lot of waste energy and heat. But the problem here is that if you try and stick too many little switches in one small area with that heat, it'll melt your computer chip. The good news is that there's a solution for this, and it's something called spin. Spin is a property of electrons, which can point in any direction. I study systems where these spins want to all point in the same direction. But if you hit them with a laser like I do in my research, you can generate something called a spin wave. In a spin wave, the spins change orientation while the electrons keep on doing whatever they were doing before. I study things like the lifetimes of these spins, how fast they move, how quickly we can switch the orientation, because the idea is that we could use these spin up waves to represent a 1 and a spin down wave to represent a 0. This will let us do computations in a much more energy efficient manner than with electronics. Going back to the traffic jam analogy, you think of if electronics is a traffic jam, in a spintronic system, you're cruising down the freeway and all you have to do is toggle your headlights on and off to get the same sort of thing. So this will let us make much faster, more powerful computer chips. We can even step back and look at the bigger picture. These spin waves don't have to live in just one dimension. It turns out they can actually live in complex textures and patterns that live in multiple dimensions. With this kind of unprecedented control we'd have at the electronic level, we could imagine designing a whole host of spintronic devices like incredibly high density data storage, or even quantum computers that can do in days the sort of calculation it would take a normal computer millions of years to carry out. So the hope is that if we can understand the properties of spins, we can spark a new revolution that will last for decades to come. Thank you.